And I think we are live. Not. 1 second. Yes. Welcome, everybody, to our 26th episode of Ask an Astronomer. We are PhD students from the Institute of Astronomy in Cambridge, United Kingdom. And we're here to answer all your questions about astronomy, science, everything you want to know, basically. So just go, if you're watching this on YouTube, you can just ask us in the YouTube chat, or if you are on Periscope, in the Periscope chat, or if you are not on these platforms or don't have an account, you can also go on Slido, that's sli.do, and enter the code #astronomy, and then ask us questions there without having to create an account. And we'll just go and answer your questions, and yeah, whatever you want to ask us. With me today, I have two students, Kat and Chiara. Do you want to introduce yourself? Maybe, Kat, do you want to start and say a bit what you're working on, who you are?
Sure. So I'm Kat. I'm a third-year PhD student at the Institute of Astronomy, and my research is focused on the effect that impacts by asteroids and comets have on the atmospheres of planets a bit like the Earth. Yeah, so planet stuff.
And Chiara?
Hi, I'm Chiara, and I'm a second-year PhD student at the Institute of Astronomy in Cambridge. And I study the planet formation. And to study planet formation in particular, I focus on the protoplanetary disks that are the planet birthplaces. So that's what I study.
Oh, very nice. So we have quite a, I would say, quite a planet expertise here. And then people will tell me that that's not actually true, but yeah, I think you're quite good at planets, better than me. I'm doing cosmology, so I'm looking at kind of the first few million years of the universe, so at the Big Bang and how the universe evolved, maybe how the first stars formed. That's kind of my area, and everything on the large scale. So the cosmic microwave background, or the kind of cosmic web that the galaxies span. And to start with, while you're all surely typing questions in the chat, I'll get one of the questions from last week, which was actually no, we have a question from Twitter already, which was asked us whether or not the satellite for a planet, like something like a moon, could also be made out of gas. And I heard, Kat, you might know this.
Yes. Yeah. So this is a really cool question. Like if we look at our own solar system, we see quite a wide variety of different satellites. So we've got our own moon, which is kind of boring and rocky, and it's not got an atmosphere. It's quite big, but it's a bit dull. We're kind of unusual in only having one moon. Like quite a lot of planets have more than one moon. Mars has 2 or 3, but they're quite small. Then you go to Saturn and it's got 50, 100, loads of moons, depends how small you go. And some of them can have kind of atmospheres. So Titan's moon, Saturn, has an atmosphere about the same mass as the Earth. So it's got quite a lot of gas, but still by mass, it's kind of 99.99% rock. But there's kind of a pattern there. So the bigger your planet is, the bigger the moon you can kind of hold on to can also be. So if you want to get a planet that's got a satellite that's also kind of like gassy in the way that Jupiter or Saturn is mainly gas, then you have to have a really massive planet. So something that's sort of several times the mass of Jupiter. And so there was one potential detection of kind of what this question is asking about. So an exomoon, so that's a moon around a planet that's not within our own solar system. And they're really hard to find because it's hard enough to find planets that aren't in our solar system. And then if you go, okay, I found the planet, I now want to know if there's a moon, that gets even harder to find. So in 2018, there was a potential detection of something a bit like Neptune orbiting something sort of several times the size of Jupiter. It was the Kepler 1625 system. But then a few years later, they kind of went back and said, actually, maybe it's not a moon. So there's no reason physically why there can't be a gas giant orbiting another gas giant, which is sort of this gassy satellite, but we've not found one yet. But that doesn't mean they don't exist.
It's a very good explanation, I think. Okay, so maybe one day we might find one. Sorry. Yeah, then we got a question from YouTube, from the Nerdy Orca, about why magnetars are considered possible sources for fast radio bursts. And now maybe I should explain what a magnetar is, and B, what a fast radio burst is. So I'll start with a fast radio burst because it's, for me at least, easier. In the universe, we have various events that basically send big pulses of energy through the universe for a really short amount of time, but very, very bright. One of them is quite well known. That's, for example, the gamma ray bursts that actually I'm not 100% sure, but basically everything that explodes in the universe makes some big kind of explosion and wave of energy. And these gamma ray bursts are really bright and can be seen from kind of very far away, and are quite well known. And now, quite recently, I think it was in 2007, if I remember correctly, we discovered the first one, which is, I guess, quite short for a science time scale. We discovered a radio burst, which is basically just a big amount of, like a large amount of radio energy coming over a really short time frame kind of through the telescope. And the reason they were not discovered earlier, I presume, is because the different frequencies of the radio wave travel at different speeds. So what that does is kind of spears out your pulse. So just imagine it as normal light, and you would imagine, say, red light would travel faster or slower than, say, blue light. Then if you would have a pulse of white light, say kind of just a flash, the red light would travel slower than the blue one. And when the pulse arrives at your telescope, it's much less, well, less flashy, kind of less bright at the same time point, but just more distributed. But people kind of initially found one of these in their telescope by looking really, watching closely, essentially, and then notice, oh, like if we search for, a pulse of energy that is distributed in exactly this way through our data, then we can find these quite easily. And now we have hundreds of fast radio bursts that we found. And the exciting thing is we have no idea where they come from, which is great. And yeah, I'm actually starting to work on this. So we have, of course, theories. I mean, that's what we do for a living, right? Put up hypotheses and theories where those could come from. And like there are various ideas like kind of mergers or binary kind of star systems. Or the one recent proposal was a magnetar. So a magnetar is basically a neutron star with a very strong magnetic field. And also, I think, not spinning quite as fast as a neutron star. And the reason we think that they could be responsible for those really far away, really strong radio bursts is because we found a mini version of those in our own galaxy. So we know there is a magnetar. We know that. We have, I think, observed this before, or at least afterwards. And we noticed a fast radio burst coming from that direction. Although it was really weak, like much weaker than the ones we see from other galaxies, but it's at least a hint. Okay, right. So basically, yeah. I mean, of course, people have also come up with models of how exactly this could work. But basically, the real reason is why we think that is because we saw a magnetar doing a mini radio burst and think maybe magnetars could also do the big radio bursts. You should know that it's the interstellar intergalactic gas that affects the speed of the waves. Yeah, indeed. So the reason why those different wavelengths, so colors kind of the radio waves, go at different speeds is because they bump into the electrons on the ray that are everywhere in the universe. And the kind of speed decrease, you could say, depends on how many electrons there are and on the frequency of the wave. Yeah, if there are any follow-up questions or something, just go ahead and write something in the chat. Okay, one more question we got last week was whether dark matter is kind of a real thing, or it's just something we made up because our math doesn't work out. Does any one of you want to comment on this, or is this another one for me?
I would add a follow-up question to that. Is just because we put it in because our maths isn't right, does that mean that it can't be real?
Yeah, I guess that's a good point. Actually, there was a conference about this at my uni in Aachen about the whole issue of, is it actually the same if we say our math isn't right and we put an extra term in our math? So let me explain this a bit more generally for everyone everyone in the audience, not just the expert in the call. So what we observed Oh, like actually like quite far ago, I think like in the 1900 somethings, 30s, I think it was Fritz Zwicky and Vera Rubin. I think those were the kind of first people who observed galaxy rotation. Well, I think one of them at least observed galaxy rotation curves and noticed. So what that, okay, what is a galaxy rotation curve? Is you look at a galaxy and look at how fast are the stars going around the center of the galaxy. And you notice the stars that are far away go much, it's faster, right? Much faster than they should be, given that kind of the mass that we see in the galaxy. And what you can calculate, either our law of gravity is wrong, or there's more mass in the galaxy than we can see. And astronomers, being very imaginative, just called the mass that there is not, that we can't see, dark matter. So we just say, okay, there is some matter we can't see, let's call it dark matter. I think a better name would be invisible matter, because it's not just kind of dark, we just can't see it. Even, you know, if the sun is behind the dark matter, it can just shine the light through us, and we wouldn't, like, we can't see this dark matter at all, if it is there. And over the time, we have actually found many effects in physics, or in cosmology in particular, that require the existence of dark matter or some mistake in our kind of calculations. And the interesting thing is, if we just assume there is this dark matter that makes up actually most of the matter in our universe, then not only this galaxy rotation curve problem is solved, but also it explains how structure could form in the early universe, and kind of how the cosmic microwave background gives us a picture it gives us. So it happens to work really well. And the alternative would be kind of modify our equations of gravity. But this would work well for, say, the galaxy rotation curves. But it wouldn't work that well for like the cosmic microwave background. And actually very hard to get this to work. So kind of non-intuitively, the simpler explanation is actually assuming there is this invisible matter, then modifying our equations of gravity. Okay, so if you have any questions about basically anything, feel free to send it to us on YouTube or the Periscope chat or Slido, sli.do, and the code #astronomy. There we go. And does every black hole contain a singularity? That's a cool question. Anyone for black holes here, or should I explain this one?
Is that not the definition of a black hole? Is that?
Well, I think a black hole is basically, well, maybe for everyone, a black hole is basically a very, very massive or dense object where light cannot escape. And I think the definition is probably something that light cannot escape. So as soon as you have a mass heavy enough compressed into a small amount of space. So let's say if you took the mass of the whole sun and shrunk it into a 1 kilometer or a few kilometers sized object, then the gravity of this object would be so strong that even light and nothing in the universe could ever escape once it gets too close to this object, which also leads to the thing being black, because no light can get out. And the question is now, what happens inside? So a theory would be, if we use our kind of equations of kind of physics, would calculate, okay, can anything withstand that pressure? And basically what you get out is nothing we know can withstand that pressure, and all the material inside should probably fall into a single point. At least that's kind of what the math tells us. I'm a bit suspicious of if that's really happening, but I'm also not an expert at all with black holes. So basically what we would say is there's a singularity, which means all the mass of the whole sun is in one kind of point, and acts as, well, a point-like mass. I'm not sure how this looks in reality, but that's kind of the idea of a singularity. And yeah, so the question asks, is there like the singularity in every black hole? And I guess the question, like more generally, we don't know, like, if there's a singularity in any black hole. I mean, there could be some force we don't know that keeps the thing from not going to a point, but just really, really small. And also, it's at the moment really hard for us to find out. So I think the working assumption for most people is we just assume it's a singularity. It doesn't really matter, because since no light and just nothing can escape the black hole, we also have no information about what's happening inside. And whatever would happen inside, it couldn't influence the outside because of this barrier. So there's no way for us, by looking at a black hole, to figure out what is inside, except how massive it is, how much charge it has, and how fast it is rotating. So basically, not much. Yeah, so for all intents and purposes, you could just calculate with a singularity in every black hole. What actually is inside black holes, no idea. And there's no easy way to find out. But thank you. It's a very nice question. So, I'll go with we have a few questions from one of the older streams that we didn't get all to answer. So I might just ask you some of them. Okay, we got one question at that one about literature recommendations. Do you have any books that you would want to recommend? Maybe in general about your field or about astronomy, or maybe about, well, something astronomy related?
Ooh, I read recently Hidden Figures, which is the story of the predominantly women who calculated the trajectories for some of the very early NASA missions, which I guess it's not really about astronomy as such, but it's a very interesting book, and it is about spaceflight, which is just inherently very cool. So I would recommend that.
Yeah, definitely agree. We got one question: has the universe rebooted before? I assume this refers to kind of the theory that the universe could kind of collapse and expand again. Problem is, it's almost as problematic as with the black hole. We have no idea what happened before the Big Bang. Basically because it was a big explosion and well, actually no. So there are certain scenarios that we could kind of see signatures of. So one kind of very let's say what friends tell me is, if we see circles in the sky in the cosmic microwave background, kind of circular patterns, something like this would tell you that a certain kind of bounce scenario has happened. So the universe has kind of collapsed at some point and then started the evolution that we know today. But we have found no hint for something like this. So of course we don't there also were many ways that this could have happened and we would never find out. So it actually, well, it wouldn't matter really because it wouldn't have any influence of our universe. And more problematically, we would have no way of finding out because it would have no influence. But yeah, we don't have any evidence that it has. And so, yeah, well, we continue with I mean, whenever you have questions, the people that are just watching in the audience, feel free to put them in the chat. Otherwise, I'm happy to take live questions here. But otherwise, I'll take this one from Reddit from the Armchair Astronomer. Questions. What's the leading theory on fast radio bursts? Okay, I assume we have this covered at the beginning of the stream. Magnetars are kind of very popular right now. Those are very cosmology-heavy questions. So if you guys want to ask anything about exoplanets, or atmospheres of exoplanets, or protoplanetary disks, go ahead and send some questions to Kat and Kiara. Do we expect dark matter and dark energy from another multiverse dimension, or do we not have the tools or sensors to interpret data in our own universe? Oh dear. Another multiverse. Yeah, sorry. I could say something about this, but to be honest, I have that little knowledge about kind of parallel dimensions and other universe theories that I'm not really confident it's saying anything I'm certain about here. Yeah, I think I'll leave it at that. I'm getting into trouble with my mathematician friends if I say anything wrong here. What else do we have?
Can I ask a question?
Oh yeah, go ahead.
Kiara, you said you do stuff on protoplanetary disks and how we get planets in them. How do you turn a disk of stuff into a planet?
Oh, that's a very interesting question. So first of all, just in general, protoplanetary disks are disk-shaped structures that form around the newborn stars. So in some sense, we can say that they are the leftover of the star forming process. Those disks are made of dust and gas in different quantities. Usually there is much more gas than dust. And it is believed that planets formed from this material. The exact process is being still studied, so there isn't a definitive answer, but there are a few theories, and the most popular ones are two. One of them is called core accretion theory, and the main idea is that the dust component in the protoplanetary disk step by step grow in size. So you start from a very small dust grain, which starts to collide and stick with other small dust grains, and then it grows more and more until reaching the size of a planet. So in this way, you can form rocky planets like Earth. The other main idea for forming gas planets is the gravitational instability theory. So the idea is that if in the protoplanetary disk you have a lot of gas, you can have this disk to become unstable in some way. And so the disk could fragment. And as a result of this fragmentation, you have a lot of fragments of gas that might be the starting point to form a gas planet. So those are the main ideas.
Exciting. So like the second one would form something like Jupiter or Saturn, like the big ones.
Yeah, yeah, that's the idea.
Cool. Thank you.
Actually, I just noticed we got one question submitted on our website. The solar wind is harmful for astronauts in space. The Earth is protected by its magnetic field from these harmful rays. So why not fit a bar magnet or suitable strength back to the astronauts? Why don't you use basically a magnet to protect the astronauts that are in space? That's actually a really good question.
Yeah.
This protects. Yeah. So actually, what's actually really nice to know. So the magnetic field of the Earth is much weaker than an everyday magnet. I mean, you can see this by taking a piece of metal. It doesn't move very strongly in the Earth magnetic field. Like if you want to use a I forgot the name of the thing that points to north. Anyway, that's like really hard to you need a really well moving needle in order to have it point according to the magnetic field of the Earth, while kind of an everyday object can move heavy metal items. Correct me if I'm wrong. I think the answer might be just that the Earth magnetic field has just much more space. So basically, when particles from space, like cosmic rays, solar wind, etc., those are charged particles, and when they are inside a magnetic field, they get deflected to the side. Like if they are, well, there's like this three-finger rule which tells you, but don't worry about the math and the details. Basically, when you're inside a magnetic field and you're a charged particle flying, then you will get deflected away from, along the field lines, actually. So, and this is proportional to the strength of the field. So when your field is 10 times stronger, then your deflection will be 10 times stronger. But also, the Earth's magnetic field is huge. It goes out far. I don't know actually how far it goes out, but it must be far above the atmosphere. So when a particle comes close to the Earth, it has hundreds of kilometers to kind of get deflected away. While if you're an astronaut and you're holding a bar magnet in your hand and the particle comes flying, it has to basically, the short distance where the field of your bar magnet kind of starts to be significant. It has only a really small part of space to be deflected. So actually, I think in order for this bar magnet protection to be strong enough, you would need a ridiculously strong magnet. I'm not sure if we can even produce magnets. Actually, it's a good question. I have no idea.
Even if we could, I'm not sure we'd want to put them next to all the computers on the space station.
That's a good point. Yeah. Right. So I assume So in the Large Hadron Collider in CERN, there's basically a big ring that accelerates particles to close to the speed of light, which evidently have strong magnets that can deflect really high energy particles. But also those magnets require the energy of a small city and cooling of quite close to 0 degrees Kelvin, the absolute 0 point. So I think that's not easy in practice to do on a space station. I have one question here, which, actually we got a question on Periscope from XEvis. Can you explain the relation between galactic neutral hydrogen and dispersion measure based on a fast telescope found this year? So actually, I'm not aware. Well, I mean, I'm not sure which measurement by the fast telescope. There's a really large telescope in China. Actually, there's a really interesting telescope. Let me maybe. I don't have a picture of this, I think. You might be aware of the Arecibo telescope, which actually got quite damaged recently and is probably going to be torn down, which is quite sad. But the Arecibo telescope is or was like a large kind of telescope built in a natural, I think, sinkhole. So they have I think a few hundred meter, like 300 or so meter wide dish, basically built in this valley. And basically in China, the fast telescope is a very similar model. Oh, the M for dark matter, not for dispersion measure. Thank you for the correction. So they have with a very similar telescope. So basically they just have kind of a nice valley, have a bit of support, and build a huge kind of telescope dish with a detector at the top. And the good thing about such a huge telescope, it's really sensitive to really kind of small signals. And it's also a radio telescope, so this could be used for finding those fast radio bursts. And so this, right, okay, actually I'm not sure what this find is, if the M stands for dark matter then. So what you can do with those radio bursts is, as I said, you can measure how many electrons there are on the way between the source and you. And when you look at some object and you can measure how many electrons are on the ray, you can basically calculate what's the density of normal matter, because all the normal matter has electrons. You know, hydrogen has electrons, helium has electrons. And basically everything except hydrogen is not really relevant, or hydrogen and helium. Everything else is really rare in the universe. So you can calculate how much normal matter there is. And then from the kind of rotation curves mentioned before, so from looking how fast stars move, and probably other measurements, I'm not sure if we can use lensing in our own galaxies, but there are various other methods to measure how much matter there's around. You could compare those two numbers to calculate how much dark matter there is in the Milky Way, or anywhere for that matter. But I guess the Milky Way is particularly interesting. Although I'm not sure what the result of that experiment was, or of that observation, because I didn't read this. Oh, we got a nice question on Slido. What is the moon made of? Asked by Margot, age 9.
I might jump in on this one. Not cheese, sadly. This is a really great question, because it turns out that the moon seems to be made of pretty much exactly the same stuff as the Earth, which you wouldn't necessarily expect. So if you think about all the moons in our solar system, so we've got our moon. Mars has some moons that look like they're kind of captured asteroids. So there's 3 main ways you can make a moon. You can either capture an object that's sort of flying around in space and it comes close enough to your planet that it ends up trapped orbiting around it. So they're called captured moons. So they're like Mars's moons. Neptune's moon Triton has a sort of an orbit that goes like almost backwards, so it looks like it's captured something that came in from the Kuiper belt, so like a comet. You can also form moons kind of in situ, so at the same time as you form your planet in your protoplanetary disk, as Chiara explained earlier, you can also form moons in the little bit of the disk that's around the planet. So they're kind of called co-accretion moons, or moons that form at the same time. And then the third way you can form a moon is probably how we formed our moon, which is the kind of the giant impact theory. So this is the idea that there was what was like a very young baby Earth, and then there was something maybe the size of Mars, and they crashed into each other about 4 billion years ago. And what that did was kind of destroy the Mars-sized thing, which we sometimes called Theia, to give it a name. So that crashed into the proto-Earth. It was destroyed. It sort of melted a whole bunch of the Earth. It was very, very disruptive. And what you end up with is a sort of another disk of kind of molten rock and gas around the proto-Earth. And some of that sort of falls back onto the Earth and forms the Earth as we know it, and the rest of it ends up forming the moon. But what this means is that the surface of the Earth and the Moon seem to be made of pretty much the same stuff, which is quite unusual because if you look at all the different sort of rocks in our solar system, they all look kind of different. So you can sort of plot them on graphs of like one composition against another composition, and they're all over the place. And then the Moon and the Earth are right in the same place, which is quite interesting. So yeah, the Moon is made of rock like we are. But
yeah, it sounds almost a bit boring, but the story is very nice.
Yeah.
But it's like, so there was this kind of excitement about kind of helium-3 or something on the Moon, or like what was it, like something used for fusion?
Water. Is it water?
Water. I mean, what is
water
water?
found on the Moon. Water sounds very boring. There was water found on the Moon recently, and that was really exciting.
Oh, okay.
But the helium is also exciting because there's not much of it, or there's not much helium-3, and we keep using it.
We got a comment, I guess, from Periscope that it's very difficult to capture moons or a space probe without some other effect. Actually, yeah, that's a cool thing. Did any one of you look into the mass of capturing kind of, let's say, an alien would send a Voyager or something like a space probe to us? How or if we would be able to catch it without, pulverizing it?
Capture is actually quite rare in kind of two-body collisions. You're much more likely to just eject the thing that came in. So there used to be loads more stuff in our solar system, and most of it has been ejected, mainly by Jupiter.
Do you want to explain how this works? Like, why does stuff get ejected by Jupiter? Like, does Jupiter just not like everything else?
Jupiter's really big. This is it's the same way we got the Voyager probes to the outer solar system. So it's this thing called like gravitational assist or slingshot trajectories. So this is the idea that you can kind of exchange some gravitational energy for kinetic energy by getting really close to a planet, sort of just grazing it, and then you get sort of pinged out the other side, going really, really fast. So we use that quite often when we're sort of sending spacecraft far away, because it's much faster than just burning a rocket and pointing it in the direction we want to go. And if we can get some help from the other planets, then why not use it? But what this means is like when asteroids are scattered or comets, they're much more likely to end up being ejected, so kind of kicked out the solar system, than they are to be captured. But if you have enough stuff, you can capture some of them. So, for example, Triton around Neptune is quite probably a captured object. Yeah.
Okay. We got one really cool question from Reddit, which is, what is some of the most mind-blowing material you have learned? So go ahead and give us the most mind-blowing things of like recent years.
What's really interesting?
Of course, it's a really hard question because I was asking for the most. So if anyone, you can also go with the rather more mind-blowing things.
There's a planet that's made up like almost entirely of just lava.
Oh.
That's really cool. It's a rocky planet, and it's really, really close to its star, and its star is really, really, really hot. And so because it's really close to its star, it behaves a bit like the Moon does. So it's tidally locked, which means it has one face that always points towards the star and one side that always points away from the star. So the side that points towards the star is really, really hot, and so hot enough to melt the rock on the surface. So you've got a sort of an ocean on this planet that's just made of melted rock. And that's kind of flowing round onto the dark side of the planet, which is cold enough so it kind of solidifies. So you've got like we have a water cycle on Earth, but with rock on an exoplanet, which is really cool.
That's amazing. That's really nice. Yeah, to be honest, most of the cool things, well, actually many of the cool things I've learned in the last years were kind of like here and other outreach events where just people were telling me all their cool stories. Otherwise, I think it's basically like kind of, well, whenever you like kind of try to think about the scale of things in cosmology or astronomy, it's just completely mind-blowing. Actually, the part about black holes, actually, I think that's nice. How fast or slow black holes evaporate. So when you have a black hole, it doesn't stay there forever. It loses energy kind of slowly. And without trying to go into the details, the more kind of curved spacetime is around a black hole, the more it loses energy. So a small black hole curves spacetime much more strongly at kind of a point than a large one. A large one has a kind of larger effect in general, but it's kind of quite large and kind of a slow transition. So smaller black holes actually evaporate much, much more than large ones, and they kind of evaporate within nanoseconds, or like even less, depending on how small they are. So when you have small black holes, you could maybe from the early universe there could be small black holes that have existed. They would have been like almost like super fast, but they would have been disappeared. While a large black hole, like a sun-sized black hole, or a black hole like in the center of the Milky Way, would live like for billions or millions of years, like super long. So that's such a large like difference. This is really surprising. Do you also have something, Chiara, or should we go to the next question? Otherwise, no, I think we got a follow up on the black holes.
Can I ask a question to Kat?
Yeah.
So you told that you study the atmospheres. So I was wondering, how can we have information from other planets' atmospheres?
Yeah, so this is really cool. So I cheat and I study the Earth's atmosphere. I'm very adventurous. I study Venus and Mars because they're quite close and we can point telescopes at them. And sometimes we can send probes. But for exoplanets, we have to be, that's a little bit harder because they're very far away. And the thing about planets is that they tend to be next to a very bright star, which means that when we point our telescopes at them, pretty much all we see is the star. So it was only kind of within the last 50 years that we were able to find planets at all. And now we're looking at it and saying, well, actually, I want to see what's on that really thin layer of gas around the surface of this planet. So we're getting better at studying the atmospheres of gas giants because they have really massive atmospheres and they tend to be quite big. So we have kind of two main ways of studying the atmosphere of a planet, and both of them rely on looking at the spectra of light coming from the system. So like looking at light at lots of different wavelengths. And if you can see where there are bits of light missing. So if you look at the light that comes from the star that goes through the planet's atmosphere, and some of that light will be absorbed by molecules that are in the atmosphere of the planet. So depending on what your molecule is, it will absorb light of a different wavelength, which means that if you look at the light coming through and you can see what's missing, you can kind of infer what's in the atmosphere. So that's something we call transmission spectroscopy. And then the other one is emission spectroscopy. And that's if you've got quite a bright planet or a dim star. And that's when you look at the light that's directly emitted by the planet itself. So you can do exactly the same thing, except you're doing the sort of reverse. So instead of looking for bits of light that are missing, you're looking for light that's emitted by molecules in the atmosphere. And so that can tell you kind of not only like what there is in your atmosphere, but it can also give you an idea of how much atmosphere you've got, which is useful for kind of working out where it might have come from. But we're getting better every time we build a better telescope, we get better measurements.
Oh, interesting. Thank you.
Thanks. Speaking of telescopes, we got a question on Periscope that now that Arecibo is decommissioned, are there any other telescopes that we can do radar astronomy with? So radar astronomy is like sending out a radar pulse to something, seeing it come back and like observing this instead of something that the object naturally, like instead of things that are basically shining themselves. I think there are like other smaller radar telescopes. I'm not sure how good they are or like how strong. I suppose Arecibo must have been really good, like probably better than others. But yeah, I'm not sure. Like I'm pretty sure that we have others. I'm just not sure how good they are. We got another YouTube question. Can black holes change their formation and their form and size, I suppose? And when does this happen? Are there like black holes that are not spheres?
Do they not get bigger when they swallow more stuff?
Yes, yes. So the size is directly related to the mass. So if you have a black hole that's double as heavy, it has a double radius. So when a black hole eats, gas that's falling in or whatever, it will grow in size. I think the form is a harder question. I'm not sure. So if a black hole, like mostly we would say, like we said this earlier, when we have a singularity, just a single point, the black hole would be kind of directly like a perfect sphere. But I suppose otherwise you would still assume that whatever is inside a black hole is probably spherical because it's really like strong gravitational force. So it will probably be a sphere. I'm not sure about spinning black holes. So if a black hole spins, it's called a Kerr black hole, and it might be not completely spherical. At least the kind of event horizon is a bit funky in those cases. Oh, we got a nice question here on YouTube. Why does the moon appear in daytime? Who wants to take this one?
I'll have a shot if you like. So this is where I really want a diagram. So like the Earth is going around the sun and the moon is going around the Earth. And the moon goes around the Earth once every 28 days. The Earth goes around the sun once every year. And then the Earth spins on its axis once every day. So we've got kind of 3 time periods. We can ignore the years for now because we don't really care about that. So we've got 2. We've got the Earth goes around in a day and the moon goes around the Earth in a month. And the other thing to know is that the moon always points the same face at the Earth. So it's tidally locked. So that means that we always see the same bit of the moon, but depending on like where the sun is in the sky, that tells us, or that will illuminate whatever half of the moon is pointing at the sun. And that's why we see kind of new moon, crescent moon, half moon, full moon. So that depends on whether the sun is kind of, it goes sun, earth, moon, and that's when we get like a bright full moon. Or if the moon is between the Earth and us, we get a new moon. So that's when we can't see any of the moon at all. And then if the moon is kind of at 90 degrees to us, we get a half moon. And that happens whether or not we're on the bit of the Earth that's in the dark or the bit that's facing the sun. So you can imagine there's a situation where sort of the moon is maybe just offset. So it's kind of offset from the sun, but it's kind of in the sun half of the space from Earth. So if you're standing on the side of Earth that's facing the sun, you'd be in daylight. But if you look kind of away from the sun, you'd be able to see a bit of the moon that was illuminated by the sun as well. So that's when you see a moon in the daytime. The reason you don't see it as often is because if the moon gets too close to the sun, it's so dim compared to the light from the sun that you just can't see it. Like it's there, but you're not going to be able to see it relative to how bright the sun is. And the only exception to that is when you get a lunar eclipse, which is when the moon passes directly in front of the sun and blocks out some of the light. And then you see it really, really obviously.
While you have the diagram, in the air, we got a question, why can we see Venus from Earth?
Okay, can I answer?
Yes.
So I think that we can see or we cannot see an object in the sky depending on how luminous it is and how distant it is. So just to give you an example, imagine to have a very, very small light bulb in your room. Then if you look at that light bulb and you are very close to the light bulb, even though it's very, very small, you can see it. But if you go far away, for example, in the kitchen, you are too far and you can't see it. Then if you take a similar light bulb, but much more luminous, you can see it both from your room and both from the kitchen because it's very luminous. So basically, we can see Venus, even though it's not hugely luminous because it's close enough to the Earth. And we can see, for example, some stars that much farther away than Venus because they are very luminous. But if we take Venus and we imagine to put it as far as another star, we couldn't see it. So basically, when you see an object, it's because there is the right combination of luminosity and distance.
Yeah, that's a very, very good explanation. So it's actually also quite similar with say, the galaxies. Like when you look into, when we look at stuff that's far, like really, really far away, we can't see single stars. We can only see kind of galaxies, just because galaxies are so bright. Or even further away, we can only see quasars, because those are like really, really bright objects that we can see that far. We got more questions. Oh, that's interesting. How does it rain diamonds on Saturn and Jupiter? Does it rain diamonds there?
So it could possibly. This is what happens when you get things that are really, really, really dense. So at really, really, really high pressure. So Saturn and Jupiter are absolutely massive. And that means that kind of by the time you get into the center of Saturn and Jupiter, like on Earth, at the surface of Earth, we currently are experiencing 1 bar of pressure. So that's a whole atmosphere is pressing down on top of us. And that's fine. Like we're happy with that. If you go to space, there's obviously no atmosphere. But if you go deeper and deeper into Jupiter or Saturn's atmosphere, the further down you go, the more pressure there is. So it's kind of analogous to going further and further down into Earth's oceans. Like by the time you get to the bottom of the Mariana Trench or whatever, the pressure is massive, and that's why all the fish there kind of look like blobs. But sort of multiply that by factors of hundreds and thousands, and that's what you get when you go further and further into gas giants like Jupiter and Saturn, and elements that behave one way on Earth that we're used to them behave very differently in kind of at those really intense pressures. So there's possibly like a core of liquid metal inside these planets. We really don't know. That's kind of the interesting thing. We have no idea what's inside Jupiter. But one of the theories is that you can end up with carbon in the form where it rains from higher up in the atmosphere down towards the core in the form of diamonds. So that's where this kind of diamond rain idea comes from, I think.
Okay, we got a couple of questions again on Slido from Margot again. If there's water on the moon, you just mentioned that there might be, what stops plants from growing there?
Because when I said there was water on the moon, there's quite a small amount of ice on the moon. It's not very nice water. And some of the other things that plants need, like carbon dioxide, so that they can photosynthesize, and for it not to go from kind of really, really hot in the daytime to really, really cold, are not there. The moon is actually quite nasty. The moon also doesn't have the atmosphere that Earth does to protect it from all of the kind of nasty radiation in space, which is also quite bad for plants. So it's good news for people who want to kind of use the moon as a staging post for missions to Mars, because it's quite easy to get to the moon, comparatively speaking. And you can then kind of build more stuff on the moon, get some fuel on the moon, and then go from the moon to Mars. And that's much easier than trying to go straight from Earth to Mars. But it's not really a nice place to be.
Okay, and Robbie, at the topic of the moon, we got a question: if the moon orbits every month, if the moon orbits Earth every month, why is a solar eclipse not happening every month? Does one of you want to answer this?
I can do it. So for a lunar eclipse to happen, we need the kind of the sun and the moon to line up kind of exactly in the right orientation, and that kind of, it happens maybe more often than you think. Sort of quite often they're not visible from anywhere where there's any people. So if you imagine, you only see the lunar eclipse if you're on the bit of Earth that's between the sun and the moon and you. And so
yeah, I think the comment mentioned it's supposed to happen every 18 months.
So I'm not quite sure about the exact timing. I know that sometimes the moon gets between the Earth and the sun, but it's not directly in front of the sun, so it kind of just misses and we don't get a lunar eclipse. So what we'd call a total eclipse is when the center of the moon passes through the center of the sun. And they're relatively rare, particularly kind of in places where we can see them.
Yeah.
So I don't know whether they do happen.
Yeah, I mean, the exact time is not, but I guess that important if you have the business of predicting lunar eclipses. No, solar, what lunar? One of them. Solar eclipse.
Yeah, right. So a lunar eclipse is the other way around. So it's when the Earth gets between the moon, and that makes the moon go a funny way. And then a solar eclipse is when the Earth goes between the moon and the sun. Sorry, the moon goes between the Earth and the sun and blocks out the sun.
Okay, we got one more question from Slido. How does an atmosphere work? Why does it look like a shell from outer space?
Ooh, that's kind of a function of gravity. So that's the same reason as to why kind of most planets are pretty much circular, is that if you kind of leave stuff to its own devices under gravity, it will form a sphere shape, because that's the shape where most of the stuff in your object is as close to the center as it can be. So it's the most stable, lowest energy state. So if you imagine you had a cuboid planet, the bits on the corners kind of want to be closer, and they could get closer by sliding down the faces. And if you just keep doing that, you end up with a circle or a sphere. And so atmospheres do the same thing, except they do it even better because they're kind of quite fluid. They can move really easily. And so if you just dump a bunch of gas on one side of a planet, it will kind of all flow around the planet to form a nice sort of circular spherical atmosphere. With the exception of things like comets that are going really fast, or things that are going very, very close to their star very fast, which can kind of lose atmosphere in a tail.
Right, yeah. We got one question on YouTube about asking if you're all in grad school. I guess that's what it's a bit different in Europe/UK from the US system, where we're doing usually you do like a bachelor's or master's degree, and then you do approximately 3.5 year PhD. So that's the kind of the phase we are in second or third year respectively. And the question asked about if anyone wants to tell about any projects that they're doing currently. And does any of you want to tell about some of your recent work?
Yeah, I could. So, as I said at the start, I look at the effect that impacts by small bodies have on terrestrial planet atmospheres. So I started off looking at the Earth because we know loads about the Earth. And so at the moment, what I'm looking at is kind of what happened to Venus and Mars in the first sort of 500 million years of the solar system, but then also looking at, as a kind of a side project, which might explain why I was so keen on all the moon questions earlier, what happens to some of the moons in the solar system if you hit them with comets. So, for example, Titan, one of Saturn's moons, has a really massive atmosphere, but then there's quite a similar moon around Jupiter, which doesn't. It's got no atmosphere at all, despite being kind of the same size and shape. So I've been looking at kind of what impacts due to those atmospheres.
As I said at the start, I study the planet formation, and the way in which I study planet formation is by studying the protoplanetary disks, that are those disks around the star. And currently, what I'm focusing on is the interaction between a newborn planet and the disk, because when you form a planet in the disk, it is possible that the planet kind of create a ring without material inside the disk. So it basically carves a gap. And so okay, so you can see here in the picture, the red areas are the areas where there is the material, while the dark areas is the areas where there isn't any material. So for example, it is very clear on the right that you have some area within the disk where there isn't the material because it's dark. And it is possible that this absence of material is due to the formation of a planet in this area, and the planet interacting with the disk because of gravity and other forces creates this gap. So what I'm studying now is this. So is how the planet formed this gap and why, and what changes when we have different planets and this kind of stuff.
So basically, it's like when you take a magnet and go through a, I don't know, a thing with lots of nails, and the magnet will attract all the nails. That's kind of how it works with the planet and gravity, I assume. It goes through the disk and just attracts, like hoovers everything in. I think my analogies are not really correct, but kind of.
Yeah. I mean, yeah, in some part works like that, but there is also another effect which actually works in the other way around. So basically, the planets tend to push away some material from its location due to some other gravitational interaction. But it's definitely true that part of this material is actually taken by the planet. So. Yeah.
Oh, that's really cool. I didn't know that it also pushes stuff away. That's interesting. Yeah, makes sense. Okay, we just got a question on YouTube asking us to answer the question. Yes, we're having about 5 minutes left. So whenever if you want some questions answered, please go ahead and send them, and I'll come back to the. I have 3 questions on my list that were answered that we will come back now. If the universe is potentially infinite, can we safely say that other intelligent life exists somewhere within it?
Not sure I'd safely say anything. But...
Well, I mean, if the universe is really infinite, then I'm pretty sure, I assume. But also, if it's really, really far away, then we'll never hear of it, and it's kind of boring life.
True.
And so maybe to clarify this, sorry, I kind of cut you off. Do you want to?
I was just going to say I'm more excited by non-intelligent life elsewhere in our solar system. At least we might be able to touch that one day.
Yeah. Okay. So what I wanted to say about the kind of size. So yeah, I mean, if the universe is infinite, like infinite is a strong word, right? It means it goes on forever and ever and ever. Then there will be everything in the universe, because it's just like if it's not the same everywhere, then something you will find everything somewhere in the universe. The question is just we can only see, at about a few tens of billions of light years, like the observable universe. So everything that we can observe from the universe, actually like so everything that could have in the past done anything that would have affected Earth. So anything whose light or what's light we would see today is at most 90 billion light years away today. Like we can't see further than that. And even in the future, there's a limit to how far we can ever reach in the universe. And basically everything beyond that is kind of not really that interesting, because we would never, if the theory of relativity and the speed of light limit holds, we will never be able to go further than this limit, which means life beyond there is kind of, we won't reach it, so it won't have a big effect. But yeah, otherwise, technically, it would exist. But of course, it could also be that the universe is not infinitely. It could also be that the universe is curved and actually kind of like a sphere and is only finitely large, and that we might be the only life in the universe. Sounds a bit sad. I think there's other life in the universe. Probably not in the galaxy. Well, maybe. Actually, after the Venus story, I'm not that sure anymore. Okay. 2 more. We got more questions. About solar wind, there was one. Can you elaborate on solar wind? Does anyone here know what solar wind is? Because I don't really.
So it's kind of, it is what it says on the tin. It's wind that comes from the sun. So it's really easy to think of the sun as just like a boring ball of burning gas in the sky.
A boring ball of burning gas in the sky.
Yeah, that's one of those. There's loads of them. No, but it does sort of many more things than just turn hydrogen into helium. So the solar wind is sort of this constant stream of sort of charged particles, so mainly electrons and some protons, sort of that just are sort of constantly streaming out from the sun out into the solar system. And they go super, super fast, like hundreds of kilometers a second. And they're really hot. So it's kind of like plasma flying off the sun. And so it's fine for us on Earth because we have this magnetic field that, as Stefan said earlier, kind of deflects the particles around us. So we kind of don't see them here on Earth. But if you're out in space, you do see them. So there was kind of some news a few years ago when one of the Voyager probes finally got far enough away from the sun that it couldn't feel the solar wind anymore. So that's this thing called the heliopause, which is where it's kind of the solar wind stops and it's like way out beyond Pluto, which is quite exciting.
Yeah, cool, okay. And if I didn't miss any question, let me know if I missed any questions. We're having the questions about pulsars. Can you tell about pulsars and what types of pulsars there are? So, well, I'm not an expert on like, small stuff in the universe, so take this with a bit of caution. But basically, pulsar or a magnetar or all these kind of objects are all neutron stars. So what happens when a big star basically like runs out of fuel and kind of dies is it usually kind of at first expands and burns a bit of bonus helium or hydrogen and eventually collapses into a really small object. And if the star is massive enough, this object will be a black hole. And yeah, I think we discussed black holes. Actually, I forgot a question. What is the nearest black hole to Earth? We'll discuss this in a second. So yeah, then the star would form a black hole. But if the star is not massive enough to form a black hole, then the material collapses, but it's not so heavy that it pulls it into a black hole, but it can form a neutron star. So basically what that is, it's basically a clump of neutrons, of kind of nuclear core material, which is just really large, like a solar mass or something. So it's a really small, really heavy, and usually really, really hot material, and usually also happens to rotate really fast. The reason for this is basically if you have a kind of like a sun that's rotating, has a lot of angular momentum. And when it collapses, it has to conserve this momentum for the most part. And because the material is much closer to the center of mass, it's like an ice sport, whatever.
Ice skating?
Ice skating, that's the word. If you kind of do ice skating or any other kind of rotating sport and pull your arms closer to you, you will go much faster. And that happens basically for the star on a large scale. So the star, all the mass of the star, all the gas falls into the center and rotates much, much faster. And I think these neutron stars can rotate like much quicker than once per second. Like I'm actually not sure what the precise numbers, but it can be ridiculously fast. And you can use it for lots of interesting science. And there are various types of neutron stars depending on kind of how magnetic they are. So if they're particularly magnetic, we would call them magnetars. And I think otherwise, or in general, we would, like especially the fast ones, we call pulsars, because when you have a rotating, are there jets? I'm not 100% sure if neutron stars do have jets or not. I think they do. So basically, when the object shines particularly bright in one direction and is rotating really fast. So you can imagine it like a flashlight, like kind of like a torch rotating really fast, and the light cone kind of passing Earth once, like in very short intervals. And this kind of pulsing effect is what you can see, and what we call a pulsar. So that's like various types of neutron stars. And yeah, the question I forgot was, what's the nearest black hole to Sun or to Earth? Does anyone know?
Oh, I have a feeling. I don't know what it's called, but it's in, is it Monoceros, the constellation? It's quite close. I can't remember the exact number. That's really bad.
So is it like a binary? Is it like a sun and a black hole, or?
I'm not sure.
So yeah, I think we had this question before, and I'm not sure if we knew the exact answer back then as well. The problem with black holes is they're really hard to find because they're just there, like kind of, well, they don't do much if they don't have, like, if matter is falling into a black hole, this matter will shine brightly, and you can see it really relatively easily. But if a black hole is just kind of alone or in a very thin region of the universe where there's not much to accrete, it's really hard to find black holes, actually. So I'm not sure if we found, like, if we're sure that there's the nearest one. Kat, did you just look up some data?
Yes, I've just looked it up, and it is HR 6819, which is about 3,000 light years away in the constellation of Monoceros. But
3,000 light years.
We've just not found them yet.
I mean, for comparison, the nearest star is like a few light years. So 3,000 is still a safe distance. Don't worry. We have nothing to fear of this black hole. And I fear the question about the true nature of dark energy has to wait until next week, because that's going to be a long question, and we're already 5 minutes over time. So thank you, everyone, for watching, and thank you especially for asking questions. Thank you, too, for being here and helping me answer those questions. And have a nice evening, everybody. And yeah, see you in a few weeks. We'll see. I'll follow us on Twitter if you want to know the exact date. We'll put an announcement there. Or subscribe on YouTube, or both. Now I have to find the stop stream button.